Ladies and gentlemen, welcome back to another series of podcasts. We are in the midst of rotational mechanics, and we're not quite out of the woods. Although we've developed rotational analogs for lots of linear quantities, right? Energy, kinematics quantities, force, right? They all have their rotational equivalents. There's one that's left that we haven't touched on yet, and it's so important it gets its own chapter. And it's called angular momentum. We are not going to get into angular momentum today. We're just going to focus on the vector nature of rotation. Let's get started. If you remember at the beginning of last unit, we introduced the right-hand rule for determining the direction of angular velocity for something that's rotating. Now, for an object that's rotating, there's really only two choices, right? There's clockwise and counterclockwise. And so you see the right-hand rule illustrated here for an object that's rotating. If you were looking down at it, it would be rotating counterclockwise, right? So you can indicate that here like this, counterclockwise. Okay, we just wrap our fingers around, and when we see our right fingers, right, we wrap that around and we see which way the thumb points, and it points up-ish, right? So that would be the direction of angular velocity. Okay, well, it turns out that we're going to make that also be the direction of torque. Okay, so that the direction of torque and the direction of angular velocity are the same. So we can indicate that this way, right? We can draw an arrow, and we'll use this symbol for torque and call it a vector. Okay, so the torque and angular velocity are going to be pointing in the same direction. Let's go to the next screen and look at another example. Let's look at a disk. All right, you see the head-on view of the disk. A force is being applied to it. It's going to make the disk rotate counterclockwise, right? Counterclockwise. Okay, we have this is the R, okay, the radius, all right? And I have an edge-on view as well. And you see in the edge-on view, I've made the force be a dot, right, because it would be coming out at us. So the force is producing a torque. And I want to show you how you can use the right-hand rule to get the direction of the torque. All right, hopefully you can use the right-hand rule here yourself and see that the direction of the angular velocity and therefore the direction of the torque, okay, is to our left, right, this way, okay? And so from the head-on view, right, that's going to look like this. I can illustrate that like this, okay? And what you notice is that all three quantities, the radius, or what's called the lever arm, okay, the radius in this case is the lever arm, the force, and the torque, they're all mutually perpendicular to each other, right? They cover all three dimensions, okay? And there's a vector operation that describes this, and it's called the cross product. So what I'm going to do now is write the torque in terms of a cross product, okay? You're used to seeing the torque written like this, right? RF, okay? There's really a little more involved in that. It's a little more involved in that, but I'll show you that in a minute. So the way we write it in the cross product fashion is like this. R equals R cross F, okay? And what you do basically is you have to go in order. So you take your first finger, right, your index finger, okay, and you point it in the direction of the radius. So in this case, I would point it down, right, like that. Okay, so I point my first finger down, and then I point my middle finger, okay, I point my middle finger in the direction of the force, all right, and then my thumb will indicate the direction of the torque, okay. So if you do that here, it's really hard to do on a two-dimensional video screen, so I'm going to show this in class. But take one of these. You can either take, this is two imaginings of the right-hand rule. Right? The one I'm describing is here. Okay, so what I'm saying is that this is the R, okay, and this is the F, and this is the torque, like that. Or in the example below here, I have to change color so it shows up. But in this case, they do it a little bit differently. Right, they pick their fingers in the direction of the radius, they pick their palm in the direction of the force, and then the thumb shows the direction of the torque. One more thing to point out here, okay, the cross product is not commutative. In other words, these two are not equal to each other. You really have to go in the correct order. This is why it's important to go in the correct order using the right-hand rule. Okay, it turns out that the two are actually negatives of each other, right? So to write that more generally, A cross B, okay, is equal to the negative of B cross A. In other words, you'll just get a product that's in the opposite direction. Okay, I want to show you now another way to write the cross product, okay, in a more mathematical way, in a way that you don't do on the calculator. Let me go to the next screen. If we consider the same disk that you were just looking at, okay, but now what we're gonna do is we're gonna change the way the force is applied. So we talked before how for a force to be a torque, it has to be off center. Okay, in other words, if this force were right here, right, it would just cause the disk to translate to the right, not rotate. Okay, and I think you see that if you move this force, like right, let's put it right here. Okay, it's just going to translate. Well, what about here? Okay, well, it's going to translate and rotate, right? But what about here? Okay, what about there? Well, it's going to rotate more, right? Would you agree it's going to rotate more? Okay. Another way to look at this is to think about right here in this position where it creates the most rotation. But what if you push like this? Is that going to make it rotate? Not at all, right? So even though that point was a great position for the horizontal force, it's not a great position at all for the vertical force to be a torque. In fact, there's no torque in that position, right? Or what if you pushed on it like that, right? Would that make it rotate? It would, but not very effectively, right? So it turns out that another thing that matters in maximizing torque is the angle between, okay, and I'll do some color coding here, the angle between the applied force, so let's say that the applied force was at some awkward angle like that, right? The applied force and the lever arm, okay? In other words, that angle makes a difference too. So we have to compare that angle, all right? You can see this very practically if you look at a wrench, right? If you're thinking about a wrench, in this first scenario here, we have the force perpendicular to the lever arm, right? So the lever arm's like this, okay? That's 90 degrees. Right here, okay, underneath it, we're not as efficient anymore, right? So the lever arm in this case is only the perpendicular component between the force, the point of application, and the axis around which it's rotating, right? The axis around which it's rotating is that bolt. Okay, and then here, right, we're pretty ineffective, right? The force is almost parallel to the wrench, and it's not going to work very well that way. So, in other words, what really counts is not the radius itself. Okay, we're going to mark that with another color. What really counts is not like how far, like this distance here necessarily. That's not what counts, right? This here. What counts is the perpendicular distance, right, which is the red arrow, the perpendicular distance between the point of application and the axis of rotation, okay, which is what we call the lever arm, that right there. Okay, and so that allows us to write the cross product in a slightly different way. So we have the cross product of vectors, right, which is R cross F. Okay, torque equals R cross F. And I can write that slightly differently now, okay, as a comparison between the lever arm and the force. I can write it like this: the magnitude of R times the magnitude of F times the sine of the angle between them. Remember, sine is a maximum at 90 degrees, right? And you see here in this situation, right, in this situation, that's where it was most effective, when the angle between the two is 90 degrees. And over here in this third scenario, when the angle is approaching 0, we're getting very ineffective, right? The sine of 0 is 0. So this is another more mathematical way to write the torque. Okay, so you can do R cross F, or you can do RF sine theta, or this is, I wrote it RF sine phi. Finally, I want to point out to you that even if you're operating the wrench ineffectively, in this case, the torque is still coming out at us, right? If you use a right-hand rule, you're still going to use, you're going to point your first finger in the direction of the lever arm. So you're going to point your first finger this way each time. Right? Each time you're going to point it this way. Now you're not getting as much torque coming out at you, right? You're not getting as much torque coming out at you, but it's still, the torque is still out at us at each point. Remember that this is like a dot is like the tip of an arrow, right? You're looking at the tip of an arrow, so that's how we depict three-dimensional motion or direction on a two-dimensional sheet, right? If we were going into the paper, right, we'd be looking at the tail of the arrow, we would say X, okay? But It's not x. It's coming. The torque's coming out at us in this case. So that's torque. I want to conclude with how you work with vectors in 3 dimensions when they're a cross product, right? We worked with 3-dimensional vectors before, but we've only done the dot product. And if you remember the dot product, for example, work, right, is force times displacement, right? The product of a dot product is a scalar, right? Work is a scalar. But the product of a cross product is a vector. So you end up with a vector, so we have to keep track of those. So we're going to go to the next screen and consider 2 3-dimensional vectors that are being multiplied by each other. Let's look at that. So I've just written them out by their ijk components, and I've just labeled them a sub x, a sub y, a sub z. Okay? Basically what you're going to do is you're going to multiply every component by every other component, right? So for example, ax is going to be multiplied by bx, by, and bz. But because of the cross product, right, and I've written some of them out on the right, because of the cross product, some of those components are going to go to 0. For example, ax times bx, right, I times I cross I is 0, right, because they're parallel to each other. So the sine, right, the sine of the angle between them, right, the angle between them is 0 because they're parallel, and the sine of 0 is 0. So I cross I is 0, j cross j is 0. Whereas some other ones here, we are going to get components, right? I cross j yields a k, and so on. And remember that that cross products are not commutative. So j cross I, right? Sometimes you're going to have a j cross I that's going to be a negative one, okay, or a negative k in this case, right? So you got to keep track of that. So it turns out that you end up having lots of terms that are grouped together, and it gets a little bit complicated to keep track of unless you use a clever device that you hopefully have come across in math already, and that is the matrix or the determinant. So I'm going to show you that on the next screen. And what you're going to do is you're going to give each vector its own row. So what you do is you write it like this. You write each unit vector in its own column, okay, and then ay, az, and then the same for vector b, okay, each of its components, okay. Now when we take a determinant, what we do is we're going to group them into 3, okay. So if you want to figure out what the component is in the I direction, okay, what you do is the following. Let me color code here a little bit. We're going to do I first, so we're going to actually sort of like X those out. You're going to look at what's left, okay, so let me highlight what's left. What we want to do is this. We're going to multiply this times this, and then we're going to subtract it from this times this. All right, so what that ends up looking like is the following. It's going to be ay bz minus az by. All that's in the I direction. Now we're going to do the j component. Okay, to do the j component, I'm going to pause and clean up the determinant again. With the j determinant, you're going to cross out this and this, and now we're left with ax and bx and az and bz. And it's actually easier to visualize this if you rewrite ax and bx over here. Now what you have is let me color code again. But you have that, and you have that. So that's going to look like this: az times bz minus ax times bz. Oops, made a little mistake there. Az bx, like that, and that's all in the j direction. Okay. And finally, I'm going to let you determine what you think the k component, right, in the z direction is going to look like, right? What's the last step here? You've seen the pattern. I'm going to let you figure that out for yourself. Again, hopefully this is a review from another math class, but we're going to do some problems like this at the beginning of class. All right, there you have it, the vector nature of rotation.